We will continue with the next topic, which is high-resolution molecular perspectives on the astrophysics of galaxies, and we will have Tomo Goto, a new distance measure using the correlation between CO luminosity and its line length.
Thank you, Monica. Okay, so I arrived in Honolulu early last Sunday, and the weather was very nice, so I wanted to go running. So I opened the map of the universe, and I was around here, and I saw Honolulu Zoo here, so I thought I could go run to zoo and back. And I used my human distance estimator. And I estimate the distance from here to here is about 10 to the minus 13 per second. And I can cover 10 to the minus 13 per second in 10 minutes or so. So, okay, I thought it's an easy job, 10 minutes out, 10 minutes back. So I started running. In 10 minutes, I see no sign of zoo. That's okay, a human distance estimator has some uncertainty. In 20 minutes, it was hot, I was sweating, I see no sign of the zoo. And in 30 minutes, I still don't see any sign of the zoo, and I was actually lost somewhere around here. And by the time I get back to the starting point, I looked like this. So, it turned out my human distance estimator was underestimating the distance by a factor of 3. So a lesson learned from here is that measuring accurate distance of the universe is very important. And that's what I'm going to talk about today. I will talk about new distance measured using CO light widows and then luminosity correlation. This work was done with Sune Toft at the Cosmology Center, and then the result was recently published in ANA. I start with a little introduction. So dark energy is one of the biggest mysteries of modern astronomy and physics. And as you all probably know, 2011, those 3 astronomers received the Nobel Prize by the work they observed type 1a supernovae. And I think one of the next key questions is the dark energy time variable or not? In terms of the dark energy equation of state W parameter, this WZ part, time variable, this WZ part is 0 or not. If WZ parameter is 0, and if this W0 parameter, constant part, is -1, then it's Einstein's cosmological constant. And I picked up a state-of-the-art of the current situation, and we have a better and better understanding on the W0 parameter. We are within something like 10% or less than 10% error. But for the time variable part, WZ parameter will have still large uncertainty. To probe the variability of the dark energy, it is important to probe at high redshift. Here's the reason. This is a Hubble diagram normalized to the cosmological constant model. So this is a normalized distance modulus as a function of redshift. And then type 1a supernova data, which received the Nobel Prize, is in gray somewhere around here. And then various cosmological models are plotted in line here. And as you can see, time variable cosmological models, those 3, have larger differences at higher redshift, somewhere around here. This is naturally expected because we want to probe the variability of the dark energy. So it's easier and better to probe a larger time span by looking at higher redshift. So if we want to probe the time variability of the dark energy, we want to probe higher redshift. However, type 1a supernovae are less useful at higher redshift rather than 2 or so, because they become, even type 1a supernovae, they become too faint to be observed at higher redshift with even 8-meter class telescopes. Especially spectroscopy to determine the type of supernova will be very difficult. More fundamentally, there will be a long time delay before a white dwarf binary accretes a mass from a binary star to reach Chandrasekhar mass and explode. It takes several gigayears. So in other words, when the age of the universe is less than a few gigayears, there won't be any more type 1a supernovae. So we need a brighter standard candle at higher edge. So instead of standard candle, we need something brighter, something like a standard campfire. So what can be a standard campfire? What we focused on in this work is sub-millimeter galaxies, which are more and more easier observed at higher redshift thanks to this ALMA telescope. These are some examples of high-G sub-millimeter galaxies observed with ALMA. And as you can see, they are all detected, and some of them even have rotation curves, something like this, something like this. And then amazingly, these are at very high redshift, around 6. So what we did is we compiled large sample of sub-millimeter galaxies detected at least in one CO transition, and then compiled from the literature. And then we created the largest sample of CO detected galaxies, about 200 galaxies. And this is the largest sample at redshift 2. And then majority of the sample comes from this nice paper by Chris and Fabian, annual review paper. And I jump onto the result, and we confirmed line luminosity, CO line luminosity, line width correlation. So what's plotted here is 200 CO galaxies, and this is the CO luminosity corrected for gravitational magnification whenever possible. And then all the CO luminosity is converted to CO1 to 0 using whatever best conversion using. And then this is the line width of CO. And I should be fair that this relation was previously suggested in these papers, but we confirmed it with 10 times larger sample. Let's look at the relation in more detail. This black line is the best fit power law with parameter something like this. And then positive slope, this slope, is significance of the positive slope is 8.7 sigma. And these blue lines are connecting medians. And as you can see, the median is going up with increasing luminosity. And we also measure the correlation coefficient. And then it's the coefficient is not so large, but the significance, p-value, is very, very small. In general case, p-value of less than 0.05 is considered significant. In the case, our p-value is very, very significant. So I think we can say this correlation is very weak, but very significant. And then scatter around the best fit power law is 43%, which is consistent with what you expect from thin, randomly oriented disks. And this correlation is not very surprising because at lower redshift, we know there's a Tully-Fisher relation. Tire-Fisher relation is a tight correlation between rotation velocity of spiral galaxies and the luminosity of spiral galaxies. So, our CO luminosity line width relation can be considered high Z version of the Tire-Fisher relation. And one important point here about this relation is if this relation evolve as a function of redshift or not. So we divided the sample into high Z and low G. So the high Z is red, greater than redshift 3, and low G is redshift less than 3. And these are the best fit power laws. And as you can see in the plot, these are consist with it. As far as our data is concerned, those two lines are consistent to each other. So within this data, there's no sign of redshift evolution. If there's no redshift evolution in this relation, there's an interesting application. We could use this relation to measure the luminosity distance to submillimeter galaxies. Here's how it works. So we can measure the line width from observation, and then if we assume this relation doesn't evolve as a function of redshift, then we can estimate its CO luminosity. And by comparing this luminosity to the observed CO flux, we can get the luminosity distance. So by this way, we went ahead and then constructed the Hubble diagram to redshift 6. So this is the Hubble diagram. This is luminosity distance measured from that relation as a function of redshift. And then these big points are my data points of submillimeter galaxies. And these small ones are type 1a supernovae. And then these three lines are three different cosmological models. And at this point, unfortunately, the scatter is too large to conclude on any cosmological models. But in the near future, ALMA is going to improve the situation. And then please note that the relation, this Hubble diagram goes to a redshift around 6. In the near future, ALMA is going to detect many submillimeter galaxies. So the number of objects will improve significantly thanks to ALMA. And at least statistical part of the noise can be beaten by, by this large sample. And also, ALMA has superb spatial resolution. So ALMA's resolution at 100 gigahertz to detect CO lines of high redshift galaxies is 0.037 arcseconds in a very extended configuration. And a typical size of the known submillimeter galaxy is several kiloparsec. So this 0.037 0.2 kiloparsec is good enough to spatially resolve submillimeter galaxies at high redshift. So by spatially resolving submillimeter galaxies, we can measure inclination and magnification, and then to reduce the systematic errors of the relation. So I summarize. So we constructed largest sample of submillimeter galaxies at redshift greater than 2 from the literature. The size of the sample is something like 200 submillimeter galaxies. And then we confirmed a weak but very significant correlation between CO luminosity and line width. And then this relation have an interesting possibility. It may be used for how to create a Hubble diagram to redshift 6 and beyond. And then more details are in this paper, so please see this paper. Thank you very much. Thank you.
Question here?
So I guess that the source of the list of scatter in your relationship between the width of the CO lines and the luminosity would be the presence of outflows, inflows, mergers that, especially at high redshift, could be, could generate a lot of scatters. I mean, molecular gases have been found to participate to processes that vary from galaxy to galaxy.
Okay.
So this would clearly, this is something that changes from galaxy to galaxy. This relationship would not be, unique, or at least you will have a lot of scatter.
Right. That's we have to see. That I would say we should collect better more data from ALMA to see if that's going to happen or not.
In fact, in the Tully-Fisher relation, what is correlated to the delta V is the mass of baryons.
Right.
So maybe L prime CO is not really a good choice of total mass of baryons. So if you have only the CO line, you could have also the dust, in fact, easily with ALMA. You can have the dust. So maybe the dust would be more representative of the total variant if you have not infrared or whatever.
Yeah, that's a good point. The dust continuum is easier to be detected, so that's a very good point. Thank you.
And another source of uncertainty of the scatter in this diagram is the conversion from the different CO transitions to CO1 to CO. I wonder if you try reducing your sample only to the CO1 to CO measurements and if you get a better correlation.
Yes, we tried that, but then of course the sample size is going to be smaller, so is there a way to go back? Okay, so we tried that, right? And then I think we can go. So here we tried if you can see the different shape of the symbol. Okay. So except CO43 transition, we tried only checking the relation using the only one transition, like 3 to 2, 2 to 1, and 1 to 0. There was a significant correlation, but of course the sample size is smaller, and so and also the slope changes slightly between those samples. Right, that's the best I could do with this sample. But then, in the future, it is clearer if we can plot this with only using a single transition. Then we can rule out that uncertainty. So.
Last question there.
So I'm very interested in your result, and my question is, can we use Alma's carbon line sheet line instead of the CO? Because if we focus on higher redshift, sheet must be much lighter than CO, and it will measure the lines. Did you try this relation with C2?
Well, I didn't try it by myself in this work, but yes, that's an interesting possibility. Yeah, we should try and see if that works. Because C2 line is much stronger than those CO lines, so it's much easier to be detected. So it's a good point. Thank you.
Okay, so thank you very much. And now we come to the last talk of